Imagine a cosmic traveler that has journeyed through the darkness of interstellar space for potentially millions of years, carrying with it pristine samples of material from an alien star system. Now picture that traveler suddenly erupting with activity, hemorrhaging water at an astonishing rate while still incredibly far from our Sun. This isn't science fiction. This is the reality of Comet 3I/Atlas, and it's rewriting everything we thought we knew about objects from beyond our solar system. On July 1, 2025, astronomers made a discovery that would captivate the scientific community and space enthusiasts worldwide. The Atlas Survey telescope in Chile detected a faint, fast-moving object streaking through the constellation Serpens near the Milky Way's dense galactic plane. Within hours of initial observations, follow-up measurements revealed something extraordinary. This wasn't just another comet from the outer reaches of our solar system. The calculations were unmistakable. This visitor was moving on a hyperbolic trajectory, screaming through our cosmic neighborhood at 58 kilometers per second relative to the Sun, a speed that could only mean one thing: it originated from another star system entirely. The discovery of 3I/Atlas marked only the third time in human history that we've confirmed an interstellar object passing through our solar system. Think about that for a moment. In the entire span of astronomical observation, spanning centuries of watching the heavens, we have definitively identified just 3 visitors from the vast space between the stars. The first was 1I/Oumuamua, discovered in October 2017, which sparked intense debate with its unusual, elongated shape and mysterious acceleration. The second was 2I/Borisov, found in August 2019, which proved to be more traditionally comet-like and somewhat easier to understand. Now, 3I/Atlas has joined this exclusive club, but it's already proving to be the most scientifically valuable of the 3. What makes these interstellar objects so incredibly rare? Consider the sheer scale of space. The nearest star system to our Sun, Proxima Centauri, sits over 4 light-years away. That's roughly 25 trillion miles of emptiness. The odds of an object being ejected from another stellar system, surviving the journey through the frigid void, and happening to pass close enough to our Sun for us to detect it are astronomically small. Most objects that get flung out of their home systems simply wander the galaxy indefinitely, never encountering another star or its orbiting worlds. We're extraordinarily fortunate to witness 3I/Atlas at all. But here's where things get truly mind-bending. When astronomers began studying 3I/Atlas in detail, they discovered behavior that defied all expectations. NASA's Neil Gehrels Swift Observatory, a space telescope designed to detect high-energy phenomena across the universe, turned its sensitive instruments toward the interstellar visitor. What they found was nothing short of shocking. The comet was actively releasing water vapor, and not just a trickle. We're talking about 40 kilograms of water every single second. To put that in perspective, imagine 10 large buckets of water being poured out into space every second, continuously for weeks on end. That's the equivalent of filling a small swimming pool every few hours. Now, you might be thinking, water vapor from a comet? That sounds pretty normal. And you'd be right, except for one critical detail. This shouldn't be happening. Not here. Not now. Not at this distance from the Sun. You see, comets are essentially dirty snowballs, frozen mixtures of ice, rock, and organic compounds. When they approach the Sun, solar radiation heats their surfaces, causing the ice to sublimate directly from solid to gas, creating the characteristic glowing coma and tail that make comets so spectacular. But there's a well-understood relationship between a comet's distance from the Sun and its activity level. The closer to the Sun, the more active the comet becomes. The farther away, the quieter it should be. 3I/Atlas was detected losing this tremendous amount of water when it was still nearly 3 astronomical units from the Sun. That's roughly 280 million miles away, well, beyond the orbit of Mars. At that distance, the solar radiation should be far too weak to trigger such dramatic water loss. Solar system comets at similar distances typically show minimal activity, if any at all. Yet 3I/Atlas was behaving like it was much closer to the Sun, losing water. Like, as one scientist colorfully put it, a fire hose running at full blast. But the mysteries don't stop with water. Spectroscopic observations, which allow astronomers to analyze the chemical composition of celestial objects by studying the light they emit or reflect, revealed another surprise. 3I/Atlas is emitting cyanide. Yes, that's cyanide, the deadly poison that immediately conjures images of spy novels and murder mysteries. In chemistry, cyanide refers to any compound containing a carbon-nitrogen bond, and in space, we specifically detect CN, or the cyanogen radical. Multiple telescopes, including the Very Large Telescope in Chile, detected clear signatures of CN emission from the comet's coma. Cyanide in comets isn't entirely unprecedented. Many solar system comets emit CN as they approach the Sun. What's fascinating is that we're seeing it in an interstellar comet, providing direct evidence that the basic chemistry involved in comet formation, including the presence of carbon-nitrogen compounds, is consistent across different star systems. But there's more. Along with the cyanide, astronomers also detected atomic nickel vapor, a metallic element that's rarely observed in such quantities in cometary atmospheres. The combination of these chemical signatures paints a picture of a comet whose composition is both familiar and alien, recognizable yet distinct. So what exactly is an interstellar comet? At its core, it's a remnant from another star's planetary system formation process. When stars form from collapsing clouds of gas and dust, they're typically surrounded by a disk of leftover material. This disk eventually coalesces into planets, moons, asteroids, and comets. During this chaotic formation period, gravitational interactions between growing planets can fling smaller objects outward at tremendous speeds, sometimes fast enough to escape the star's gravitational pull entirely. These cosmic castaways then wander through interstellar space, potentially for billions of years, until by chance they encounter another star system. When 3I/Atlas enters our solar system, it brings with it a time capsule of sorts. The materials frozen within its nucleus have remained largely unchanged since they formed around an alien star potentially billions of years ago. By studying this comet, we're essentially performing a chemical analysis of another planetary system's building blocks. We're asking questions that would otherwise be impossible to answer. What elements and compounds were present in that distant stellar nursery? Was the chemistry similar to our own solar system's early days? What does this tell us about the universal nature of planet formation? The implications are profound. Every measurement of 3I/Atlas, every spectroscopic reading, every calculation of its water loss rate, adds another piece to the puzzle of how planetary systems form and evolve throughout the galaxy. The detection of water, cyanide, carbon dioxide, carbon monoxide, and nickel tells us that the chemical ingredients necessary for complex chemistry and potentially even life are not unique to our corner of the universe. They're out there, scattered among the stars, locked within countless comets and planetesimals orbiting distant suns. And we're watching this drama unfold in real time as 3I/Atlas continues its journey toward perihelion, its closest approach to our Sun. On October 30th, 2025, its activity will only intensify. The water loss will accelerate. The coma will grow brighter. And astronomers around the world will be watching, instruments trained on this messenger from beyond, eager to extract every possible insight from its brief passage through our neighborhood. This is more than just a scientific curiosity. This is an opportunity to understand our place in the cosmic story, to recognize that the chemistry of life and the processes of planetary formation extend far beyond our solar system. 3I/Atlas is proof that we live in a universe where worlds beyond our own share fundamental characteristics with our own planetary home, where the same physical and chemical laws govern the formation of stars and planets across billions of light-years of space. The night sky has always held surprises for those who watch it carefully, but on July 1, 2025, astronomers scanning the heavens encountered something that would send shockwaves through the scientific community. It wasn't a supernova, wasn't a gamma-ray burst, and wasn't any of the thousands of asteroids that pepper our cosmic neighborhood. It was something far more rare and scientifically valuable. It was a messenger from another star system, traveling through our solar system at breathtaking speed, and it was about to reveal secrets about planetary systems beyond our own. The discovery came from the Asteroid Terrestrial Impact Last Alert System, appropriately known by its acronym ATLAS. This NASA-funded network of robotic telescopes serves as one of humanity's early warning systems for potentially hazardous near-Earth objects. The particular telescope that made the discovery was stationed at Rio Hurtado, Chile, a remote location chosen specifically for its dark skies and clear atmospheric conditions. The observatory sits high in the Chilean mountains, its powerful survey telescopes sweeping across the sky night after night, photographing vast swaths of space and comparing each new image against previous observations to detect anything that moves. On that pivotal night in early July, the ATLAS system's automated detection algorithms flagged something unusual. A faint object, registering at apparent magnitude 18, far too dim for the naked eye and even challenging for many amateur telescopes, was moving across the sky, near the border between the constellations Serpens Cauda and Sagittarius. This region of sky sits near the galactic plane, the dense band of stars that marks the disk of our Milky Way galaxy. It's a crowded region, packed with stars, making the detection of faint moving objects particularly challenging. Yet the ATLAS system had found it. The newly discovered object was initially given the temporary designation A11PL3Z, a placeholder name used by the Minor Planet Center until the object's nature and trajectory could be properly determined. Within hours, the discovery observations were submitted to the International Astronomical Union's Minor Planet Center, the global clearinghouse for observations of asteroids, comets, and other small solar system bodies. But this was no ordinary submission. The initial orbital calculations suggested something concerning the object might be on a highly eccentric path that could bring it uncomfortably close to Earth's orbit. This triggered an immediate response. The Minor Planet Center temporarily listed A11PL3Z on the Near-Earth Object Confirmation page, a publicly accessible database designed to alert astronomers worldwide when a potentially hazardous object requires urgent follow-up observations. Within the global astronomical community, this listing acts like a bat signal. Professional observatories and dedicated amateur astronomers around the world immediately swung into action, training their telescopes on the coordinates provided by ATLAS. This is how modern astronomy works, a collaborative effort spanning continents and time zones, with observers passing the baton as Earth rotates and different regions gain access to the night sky. Over the next hours and days, observations poured in from observatories across the globe. Each new measurement refined the object's trajectory, each data point narrowing the uncertainties in its orbital path. And then the calculations began to reveal something unexpected. The object wasn't going to come close to Earth. In fact, as more observations accumulated, it became clear that this visitor was on a trajectory unlike any typical solar system object. The orbit wasn't elliptical. It was hyperbolic. Profoundly, dramatically hyperbolic. The mathematical distinction might sound technical, but its implications are staggering. An elliptical orbit, even a highly eccentric one, is a closed loop. Objects on elliptical orbits are gravitationally bound to the Sun, destined to circle our star indefinitely, perhaps taking thousands or even millions of years to complete a single orbit, but always returning. A hyperbolic orbit is fundamentally different. It's an open trajectory. Objects on hyperbolic orbits are moving too fast for the Sun's gravity to capture them. They pass through the solar system once and then continue on into interstellar space, never to return. The object's speed told the same story. When discovered, it was moving at 61 kilometers per second relative to the Sun. To put that in perspective, the fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at its closest approach to the Sun, but that's after falling toward the Sun from a great distance and being accelerated by solar gravity. For an object entering the solar system from interstellar space to be moving at 61 kilometers per second while still over 4 astronomical units from the Sun indicates an enormous amount of kinetic energy that could only come from one source: the object's motion through the galaxy itself. As the orbit became better defined, astronomers calculated a critical parameter called the hyperbolic excess velocity. This is the speed an object would have if it were infinitely far from the Sun, no longer being accelerated or decelerated by solar gravity. For A11PL3Z, that speed was 58 kilometers per second. This is the object's baseline speed, the velocity it had as it drifted through interstellar space before encountering our Sun. It's a speed that can only be explained if the object originated from another star system entirely. This was an interstellar object, only the third ever confirmed in human history. The previous 2 interstellar visitors provide context for how extraordinary this discovery truly is. The first, 1I/Oumuamua, was detected on October 19, 2017, already on its way out of the inner solar system. It had passed perihelion, its closest approach to the Sun, before we even knew it existed. Observations had to be rushed as it rapidly receded from us, and while astronomers managed to gather valuable data, many questions remained unanswered. Its unusual elongated shape, its mysterious non-gravitational acceleration, and its lack of visible cometary activity sparked debates that continue to this day. The second interstellar visitor, 2I/Borisov, discovered on August 30, 2019, proved to be more cooperative. It was detected earlier in its approach, giving astronomers months to study it. Borisov looked and behaved like a typical comet, with a visible coma and tail, showing that comets from other star systems can be remarkably similar to our own. It had a hyperbolic excess velocity of 32 kilometers per second, fast enough to confirm its interstellar origin, but not exceptionally so. Now 3I/Atlas, as the newly confirmed object would be designated, entered the stage with even more dramatic characteristics. Its hyperbolic excess velocity of 58 kilometers per second makes it significantly faster than either of its predecessors. It's screaming through our solar system at a velocity that speaks to violent origins, perhaps ejected from its home system by close gravitational encounters with giant planets or even stellar companions. But the excitement didn't end with the initial discovery. As astronomers dug through archival observations, they found that 3I/Atlas had actually been photographed before July 1 without being recognized for what it was. The Zwicky Transit Facility at Palomar Observatory in California had captured images of the comet on June 28 and 29, just days before the Atlas discovery. More searching revealed CTF images from June 14 through 21. Atlas itself had pre-discovery images going back to June 25. Amateur astronomer Sam Dean, known for his meticulous analysis of asteroid and comet data, identified additional Atlas observations extending all the way back to June 5. Why wasn't it discovered earlier? The answer lies in where it was located in the sky. During Much of June, 3I/Atlas was passing in front of the galactic center, the densest concentration of stars in the sky from our perspective. Imagine trying to spot a faint, slowly moving gray speck against a backdrop of thousands of brilliant lights, all of different brightnesses and colors. The comet was effectively camouflaged by the stellar background, only becoming easier to detect as it moved away from the galactic plane's densest regions. These pre-discovery observations proved invaluable. They extended the observational arc, the period of time over which the object's position had been measured, from a few days to nearly a month. The longer the observational arc, the more precisely an orbit can be determined. With this extended dataset, astronomers calculated that 3I/Atlas has an orbital eccentricity of 6.141, plus or minus 0.002. This is an extraordinarily high eccentricity. For comparison, 1I/Oumuamua had an eccentricity of 1.2, already definitively hyperbolic. 2I/Borisov's eccentricity was 3.4. At 6.141, the orbit of 3I/Atlas is so hyperbolic that it's nearly a straight line through the solar system. The comet is barely being deflected by the sun's gravity at all, simply sweeping past on a trajectory that will carry it back out into the interstellar medium. The comet's trajectory brought it into the inner solar system from a distance of 4.5 astronomical units when discovered, about 670 million kilometers from the Sun, within the orbit of Jupiter. It was inbound, heading toward perihelion, the point of closest approach to our star. Calculations showed that perihelion would occur on October 29, 2025, at precisely 11 hours and 44 minutes Universal Time, give or take about 1 minute. At that moment, 3I/Atlas would be 1.36 astronomical units from the Sun, roughly 203 million kilometers, placing it in the gap between Earth's orbit and Mars's orbit. The comet's trajectory is also remarkably well aligned with the plane of the solar system. Its orbital inclination is 175 degrees, which in orbital mechanics terms means it's moving retrograde, backward relative to the planet's motion, but tilted only about 5 degrees from the ecliptic, the plane in which most planets orbit. This alignment is purely coincidental, but it has important practical implications. It means the comet's path brings it relatively close to several planets during its passage through the solar system. On October 3, 2025, just 1 week before perihelion, 3I/Atlas made an extremely close pass by Mars, approaching within 0.19 astronomical units, about 28 million kilometers. In cosmic terms, this is a remarkably close encounter. From Mars's perspective, the comet was predicted to reach an apparent magnitude of about 11, potentially visible to spacecraft orbiting the red planet. This presented an unprecedented opportunity. Mars orbiters, including NASA's Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express, were positioned to observe an interstellar visitor from just tens of millions of kilometers away, far closer than any Earth-based telescope could achieve. After perihelion, the comet's outbound trajectory will carry it past Venus on November 3 at a distance of 0.65 astronomical units, then past Earth on December 19 at 1.8 astronomical units, safely distant and posing no threat whatsoever to our planet. Finally, in March 2026, 3I/Atlas will pass just 0.36 astronomical units from Jupiter, about 54 million kilometers, before leaving the inner solar system behind and beginning its journey back into interstellar space. At perihelion, the comet will be traveling at its maximum speed relative to the Sun, 68 kilometers per second. That's over 244,000 kilometers per hour. Fast enough to cross the distance from Earth to the Moon in just over an hour and a half. As it climbs back out of the Sun's gravitational well, it will slow down, but only to its baseline hyperbolic excess velocity of 58 kilometers per second. At that speed, it will eventually leave the solar system entirely, taking with it whatever secrets it still holds, bound for the vast spaces between the stars, perhaps to encounter another stellar system millions of years from now. The trajectory's alignment with the solar system plane creates one unfortunate consequence for Earth-based observers. As 3I/Atlas approached perihelion, its angular separation from the Sun in our sky, known as solar elongation, steadily decreased. By early October, the comet was less than 30 degrees from the Sun, visible only briefly after sunset from equatorial latitudes. On October 21st, 8 days before perihelion, the comet reached solar conjunction, passing behind the Sun from Earth's perspective. During the critical period around perihelion, when the comet's activity should be at its peak, Earth-based observations became impossible. The comet was lost in the Sun's glare, observable only from spacecraft, and possibly from Mars. After perihelion, 3I/Atlas reappeared in Earth's skies just before dawn in early November, now moving away from the Sun and gradually growing dimmer. By December, it will have faded beyond the reach of all but the largest telescopes, slowly receding into the darkness from which it came, a cosmic drifter returning to the interstellar void, having granted humanity a brief but precious window to study material from another star system. When astronomers first discovered 3I/Atlas on that July night, they knew they had found an interstellar visitor, but they had no idea just how strange this cosmic wanderer would prove to be. Within weeks of the discovery, observations began revealing something completely unexpected, something that would challenge our understanding of how comets behave and what drives their activity. This interstellar messenger wasn't just passing through our solar system quietly. It was actively shedding enormous quantities of water at a distance where it should have been essentially dormant. The mystery of 3I/Atlas's water loss would become one of the most compelling puzzles in recent astronomical history. The breakthrough came from an unlikely source. NASA's Neil Gorell's Swift Observatory, named after the pioneering astrophysicist who led its development, is a space telescope primarily designed to detect and study gamma-ray bursts, the most violent explosions in the universe since the Big Bang. Swift's ability to rapidly slew to new targets, repointing itself in mere seconds, makes it ideal for capturing fleeting cosmic events. But Swift has another capability that proved crucial for studying 3I/Atlas. Its ultraviolet and optical telescope, a modest 30-centimeter instrument that, despite its small size, can detect wavelengths of light completely absorbed by Earth's atmosphere. A team of astronomers from Auburn University, led by researchers Ashish Singh under the supervision of Dennis Bowitz, an expert in cometary science, requested observing time on Swift to target the newly discovered interstellar comet. On July 31st and August 1st, 2025, Swift's ultraviolet telescope locked onto 3I/Atlas and began collecting photons. The comet was faint, registering at around apparent magnitude 17, far too dim for the naked eye and challenging even for Swift's sensitive detectors. But the telescope's orbital vantage point, high above the atmosphere's blurring and absorbing effects, gave it a crucial advantage. Free from the sky's glare and atmospheric interference, Swift's modest aperture achieves ultraviolet sensitivity comparable to a 4-meter class ground-based telescope. The observations were targeting one specific feature, hydroxyl radicals, abbreviated as OH. When water molecules in space are hit by ultraviolet light from the sun, they break apart through a process called photodissociation. One of the primary breakdown products is OH, a highly reactive molecule consisting of one oxygen atom bonded to one hydrogen atom. This OH absorbs and remits ultraviolet light at characteristic wavelengths, particularly around 3,085 angstroms, creating a distinctive signature that astronomers can detect. By measuring the brightness of this OH emission, scientists can work backward to calculate how much water vapor is present in a comet's coma, and from there, determine the rate at which water is being released from the nucleus. When the Auburn team analyzed Swift's ultraviolet images, they found exactly what they were looking for: a clear detection of OH emissions surrounding 3I/Atlas. The glow was faint but unmistakable, the ultraviolet fingerprint of water molecules being torn apart by solar radiation. Now came the crucial calculation. How much water was this comet producing? The answer depended on several factors, including how reflective the comet's dust was at different wavelengths, a property known as reddening. Making reasonable assumptions about the dust's reflectivity, the team calculated a water production rate of approximately 1.35 times 10 to the 27th molecules per second, with an uncertainty of about 20%. Let's put that number in more comprehensible terms. 1.35 times 10 to the 27th water molecules per second translates to about 40 kilograms of water every single second. That's roughly 88 pounds per second, or the equivalent of filling 10 large buckets every second continuously. If you could capture all that water, you'd fill an Olympic-sized swimming pool in less than 16 hours. This isn't a trickle. This isn't even a substantial leak. This is, as scientists described it, like a fire hose running at full blast, continuously for weeks on end. But here's what makes this water loss truly extraordinary: the distance from the sun at which it was occurring. When Swift made its observations, 3I/Atlas was located 3.51 astronomical units from the sun. That's about 525 million kilometers, or 326 million miles. To visualize this distance, imagine the space between Earth and the sun, then triple it. The comet was far beyond the orbit of Mars, approaching the inner edge of the asteroid belt. At that distance, the sun appears much smaller and dimmer than it does from Earth. Solar radiation is more than 12 times weaker than what we experience on our planet. For typical solar system comets, this distance represents a threshold. Inside about 3 astronomical units, solar heating can become strong enough to sublimate water ice from a comet's surface, the transition from solid ice directly to vapor without passing through a liquid phase. Outside 3 astronomical units, solar heating is generally too weak to drive significant water ice sublimation. Most comets at this distance are quiet, dormant, showing minimal activity. They may release small amounts of more volatile substances like carbon monoxide, which sublimates at much colder temperatures than water, but water production should be negligible. Yet 3I/Atlas was defying this conventional understanding. The comet was losing water at a rate comparable to some moderately active comets much closer to the Sun. Astronomers quickly recognized that something unusual must be happening. The standard model of cometary activity, where solar radiation heats the nucleus surface and causes sublimation, couldn't easily explain this behavior. The Sun simply wasn't providing enough energy at 3.5 astronomical units to drive such dramatic water loss through direct surface heating alone. The Auburn team proposed an alternative mechanism. Perhaps the water vapor wasn't coming primarily from the nucleus surface at all. Instead, they suggested that small icy grains, microscopic particles of dust mixed with water ice, were being released from the nucleus and carried outward into the coma by other more volatile gases like carbon monoxide. Once in the coma, exposed to direct sunlight without the thermal insulation of surrounding material, these tiny icy grains could heat up and sublimate even at large distances from the sun. This would create what's known as an extended source of water vapor, where the production happens throughout a large volume of the coma rather than being concentrated at the nucleus surface. This hypothesis found support from other observations. Near-infrared spectroscopic measurements of 3I/Atlas, obtained around the same time as the Swift observations, detected signatures consistent with icy grains in the comet's coma. These weren't just hypothetical particles. Instruments were actually seeing evidence of ice-bearing dust surrounding the nucleus. The pieces began to fit together. Carbon monoxide, or another highly volatile substance, sublimating from the nucleus even at large distances, lifts dust and ice grains off the surface. Once free, these grains drift outward, get hit by sunlight, warm up, and release their water content over an extended region. This extended source mechanism has been observed in a handful of other distant comets, but it's relatively rare. Most comets don't show significant water activity at distances beyond 3 astronomical units. The fact that 3I/Atlas exhibited such strong water production so far from the Sun immediately placed it in an unusual category. It suggested that this interstellar visitor either had an exceptionally volatile-rich composition, a highly active surface, or both. Further analysis of the swift observations revealed another surprising detail: the implied active surface area. If we assume that water is sublimating from the nucleus surface in thermal equilibrium with solar heating, we can calculate how much surface area would need to be actively producing water to account for the observed 40 kilograms per second production rate. The Auburn team performed this calculation and found that at least 19 square kilometers of active surface would be required. That's roughly the size of 2,000 standard American football fields. But there's a problem. Based on observations by the Hubble Space Telescope and other instruments, the nucleus of 3I/Atlas is estimated to be quite small, likely somewhere between 320 meters and 5.6 kilometers in diameter. The large uncertainty exists because the nucleus is shrouded in its dusty coma, making precise size measurements difficult. However, most evidence points toward the smaller end of that range, probably less than 1 kilometer in diameter. For a nucleus less than 1 kilometer across, the total surface area would be at most a few square kilometers. If 19 square kilometers of active area is required, and the total available surface might be only 2 or 3 square kilometers, we run into an obvious mathematical impossibility. This discrepancy strongly supports the extended source hypothesis. The water production cannot be coming from the nucleus surface alone. It must be coming from icy grains distributed throughout the coma. But even if we consider the possibility that the nucleus might be at the larger end of the size estimates, say 4 or 5 kilometers in diameter, requiring 19 square kilometers of active surface still implies that over 20% of the entire nucleus surface would need to be actively sublimating ice. For comparison, most solar system comets show active areas covering just a few percent of their total surface. The rest is covered by a lag deposit, a layer of non-volatile dust and rock left behind as ice sublimates, which insulates the underlying material and prevents further outgassing. A nucleus with more than 20% active surface is extraordinarily unusual. It suggests either a very young comet that hasn't had time to build up extensive lag deposits, or a comet with some unusual mechanism for maintaining fresh, exposed ice across much of its surface. Either way, it points to 3I/Atlas being fundamentally different from typical solar system comets. The timing of the water detection also raised eyebrows. Spectroscopic observations searching for other volatiles had been ongoing since shortly after the comet's discovery. Multiple teams were using ground-based telescopes to look for signatures of carbon monoxide, cyanide, and other common cometary molecules. Yet in early August, when Swift detected strong water production, ground-based observers had not yet reported any detection of cyan, the cyanogen radical that's typically one of the first molecules observed in active comets. This sequence, water before cyanide, is unusual. In most comets, cyan appears early and prominently because the parent molecules that produce cyan, likely hydrogen cyanide or some other carbon-nitrogen compound, are relatively easy to sublimate and detect. The fact that 3I/Atlas showed strong water activity before showing clear cyan emissions suggested something about its composition or outgassing behavior was different from typical solar system comets. Perhaps the volatile inventory was skewed more toward water and carbon monoxide and less toward cyan-producing species. Or perhaps the extended grain-driven source mechanism preferentially released water while retaining other molecules. The early swift observations were capturing the comet in a transitional phase, as its activity began ramping up. In response to increasing solar heating, as 3I/Atlas continued its inbound journey, approaching closer to the Sun through August and September, its water production likely increased. Unfortunately, direct follow-up observations became challenging. The comet's position in the sky brought it into increasingly difficult observing geometries. By late September, it was low in the twilight sky, and by early October, it was approaching solar conjunction, becoming lost in the Sun's glare from Earth's perspective. Swift could no longer observe it safely, and ground-based telescopes faced impossible conditions with the comet so close to the Sun in apparent position. The water loss rate measured by Swift, 40 kilograms per second at 3.5 astronomical units, represents a snapshot in time. As the comet moved closer to the Sun, approaching its October 30th perihelion at 1.36 astronomical units, the water production almost certainly increased dramatically. At perihelion, with solar radiation nearly 7 times stronger than during the Swift observations, the comet's water loss could have reached several hundred kilograms per second, perhaps even approaching a ton per second at peak activity. Over the entire active period, from when the comet first began showing water activity at perhaps 4 or 5 astronomical units inbound until it recedes beyond 3 or 4 astronomical units outbound, probably spanning several months, the total mass of water lost could amount to millions or even tens of millions of kilograms. For a nucleus potentially less than a kilometer in diameter, losing that much material represents a significant fraction of the total mass. This interstellar visitor is literally evaporating before our eyes, shedding layers of ancient ice formed billions of years ago around an alien star, releasing that material into our solar system, where it will become part of the interplanetary medium. The detection of water vapor from 3I/Atlas carries profound implications beyond the detection of water vapor from 3I/Atlas carries profound implications beyond just understanding this one object. It provides direct evidence that water ice, the essential ingredient for life as we know it, exists not just in our solar system but around other stars as well. The building blocks of planets, and potentially life, are universal. Whatever star system 3I/Atlas came from, wherever in the galaxy it originated, that system had water-rich planetesimals forming in its outer reaches, just as happened in our own solar system's early history. The chemistry that leads to icy comets appears to be a common outcome of planet formation across different stellar environments. When we think of cyanide, our minds typically conjure images of poison, espionage, thrillers, and murder mysteries. It's a compound with a dark reputation in popular culture, associated with toxicity and danger. But in the realm of space chemistry, cyanide compounds tell a very different story. They're among the fundamental building blocks of complex organic chemistry, molecules that play crucial roles in the formation of amino acids, the precursors to proteins and potentially life itself. The detection of cyanide in 3I/Atlas isn't just a curious footnote in this cosmic visitor's story. It's a window into the chemical environment of another star system and a clue to understanding how the ingredients for life might be distributed throughout the galaxy. The quest to detect specific molecules in 3I/Atlas's coma began almost immediately after the comet's discovery. Spectroscopy, the analysis of light broken down into its component wavelengths, serves as the primary tool for identifying chemical compounds in distant astronomical objects. Different molecules absorb and emit light at characteristic wavelengths, creating unique fingerprints that astronomers can recognize. For comets, particular molecules of interest include water, carbon monoxide, carbon dioxide, and various organic compounds, including cyanogen radicals, abbreviated as CN. The Very Large Telescope in Chile, operated by the European Southern Observatory and perched high atop Cerro Paranal in the Atacama Desert, became one of the key instruments in unraveling 3I/Atlas's chemical secrets. On July 20, 2025, less than 3 weeks after the comet's discovery, the VLT turned its powerful spectrographs toward the faint interstellar visitor. The telescope was equipped with UVS, the ultraviolet and visual shell spectrograph, an instrument capable of capturing incredibly detailed spectra across a wide range of wavelengths from the near-ultraviolet through the visible spectrum into the near-infrared. The initial VLT observations revealed something unexpected. The spectra showed clear emission lines from atomic nickel, specifically the neutral nickel atom designated Ni. This was surprising not because nickel in comets is unprecedented, but because it appeared so early and prominently. Nickel had been detected in a handful of solar system comets before, including notably in the other interstellar visitor, 2I/Borisov. But, in most cases, nickel emission is faint and appears only at specific heliocentric distances as the comet warms. In 3I/Atlas, nickel was showing up strongly at 4.4 astronomical units from the Sun, when the comet was still quite far from the inner solar system. The team analyzing the VLT data, led by researchers including Rohan Rahatgaonkar and Thomas Purzia from the Pontifical Catholic University of Chile, continued monitoring 3I/Atlas over subsequent weeks. They obtained multiple spectroscopic observations between July 20th and August 21st as the comet approached from 4.4 astronomical units down to 2.85 astronomical units. Throughout this period, they watched the nickel emission grow steadily stronger, indicating increasing production rates as solar heating intensified. But nickel wasn't the only surprise. On August 14th, nearly a month after the first nickel detection, the VLT spectra finally showed evidence of cyanide. The characteristic emission bands of CN appeared in the spectra, faint at first but becoming more prominent in subsequent observations. This sequence, nickel before cyanide, struck astronomers as unusual. In typical solar system comets, CN is one of the earliest molecules detected, often appearing before many other species because its parent molecules, likely hydrogen cyanide abbreviated HCN or related carbon-nitrogen compounds, sublimate relatively easily and break apart under solar ultraviolet radiation to produce the observable CN radical. The fact that 3I/Atlas showed strong nickel emission for weeks before showing clear CN emission suggested something different about either its composition or its outgassing behavior. Perhaps the comet was genuinely depleted in CN-producing compounds compared to typical solar system comets. Or perhaps the thermal and radiative environment at its surface was releasing nickel-bearing compounds, preferentially before conditions became suitable for significant CN production. Either way, the unusual sequence hinted at compositional differences from solar system norms. By August 21st, when the VLT observations concluded, the team calculated that 3I/Atlas was producing about 17.6 grams of cyanide per second, plus or minus 2 grams. That's roughly 0.6 ounces per second, or about 35 pounds per day. While this might sound like a significant amount, it's actually relatively modest for an active comet. Many solar system comets produce cyanide at substantially higher rates when at similar distances from the Sun. The relatively low CN production in 3I/Atlas, combined with its late appearance compared to nickel, added another piece to the compositional puzzle. Independent observations from other facilities corroborated and expanded upon the VLT findings. A team using the MDM Observatory in Arizona conducted a 10-night spectroscopic monitoring campaign between August 8th and 17th, 2025, led by researchers including Luis Salazar Manzano and Xingwen Lin. Their observations, obtained with the 2.4-meter Hiltner telescope and the 1.3-meter McGraw-Hill telescope, captured what they described as the onset of cyan emission. During the first few nights of their campaign, cyan was either absent or below detection limits. But as the nights progressed and the comet continued approaching the Sun, moving from 3.2 down to 2.9 astronomical units, cyan emission gradually appeared and strengthened. The MDM team measured a cyan production rate of approximately 6 times 10 to the 24th molecules per second toward the end of their observing run. This translates to roughly similar values as those derived from the VLT observations when accounting for the different observation dates and heliocentric distances. The agreement between independent measurements using different telescopes and techniques provided confidence that the detections were real and the production rates accurately determined. But perhaps more significant than the cyan detection itself was what wasn't detected. Both the VLT and MDM teams searched carefully for emission from dicarbon, the 2-carbon molecule designated C2. This molecule typically produces very characteristic emission bands in the green part of the spectrum, often giving comets a greenish hue when they're sufficiently active. C2 is a common product in comet comas, formed when more complex carbon chain molecules break down under solar radiation. In a typical comet, you'd expect to see both cyan and C2, often with C2 being quite prominent. Yet 3I/ATLAS showed essentially no detectable C2 emission. The MDM team set stringent upper limits on the C2 to cyan ratio, finding values less than 10 to the minus 0.8. This is an exceptionally low ratio, indicating severe depletion of C2 or its parent molecules. The VLT observations similarly found no evidence of C2, nor of the related 3-carbon molecule C3, nor of various other carbon chain compounds that might be expected in a typical cometary coma. The absence of these molecules is striking and significant. In cometary science, there's a recognized classification scheme based on carbon chemistry. Some comets are typical, showing robust C2 emission alongside cyan. Others are depleted, showing weaker C2 relative to cyan. And a rare few are severely depleted, showing almost no C2 at all despite having measurable cyan. This depletion likely reflects differences in formation conditions, specifically the temperature and chemical environment in the protoplanetary disk region where the comet originally condensed. Carbon chain compounds like C2 and C3 may form preferentially in warmer regions or under specific chemical conditions. Comets depleted in these compounds may have formed in colder, more distant regions of their parent disk, or under different chemical regimes. 3I/ATLAS appears to be one of the most carbon chain depleted comets ever observed. Its C2 to cyan ratio places it at the extreme end of the depletion spectrum, comparable to only a handful of solar system comets that show similar characteristics. This severe depletion provides a crucial clue about the comet's origin. It suggests that 3I/ATLAS formed in the outer reaches of its parent star's protoplanetary disk, in a cold, possibly chemically reducing environment where carbon chain molecules either didn't form efficiently or were destroyed by subsequent processing. The detection of hydrogen cyanide specifically, not just the cyan radical, came from another set of observations. The James Clerk Maxwell Telescope, a 50-meter submillimeter radio telescope located on Mauna Kea in Hawaii, observed 3I/ATLAS on September 7th and again on September 14th, 2025. Radio observations at submillimeter wavelengths can detect the rotational transitions of molecules, providing direct measurements of molecular abundances rather than relying on daughter Products like CN. The JCMT detected HCN directly, measuring production rates of 1.5 times 10 to the 25th molecules per second on September 7, increasing to 4.5 times 10 to the 25th molecules per second by September 14. That later measurement translates to about 2 kilograms of hydrogen cyanide per second. These HCN production rates are consistent with the CN observations after accounting for the photodissociation process that breaks HCN apart into CN and hydrogen. The agreement between different observational techniques, spectroscopic detection of CN and radio detection of HCN, provides robust confirmation of the comet's cyanide content and production behavior. The observations also revealed that the cyanide coma was asymmetric, elongated in the antisolar direction, creating a teardrop-shaped cloud, extending about 180,000 kilometers across. This asymmetry is typical of active cometary outgassing, where material released from the sunlit hemisphere of the nucleus gets blown back by solar radiation pressure and the solar wind. But what does the presence of cyanide actually tell us? Hydrogen cyanide is one of the most important molecules in prebiotic chemistry, the study of how simple molecules can combine to form the complex organic compounds necessary for life. HCN is a key ingredient in several proposed pathways for synthesizing amino acids, the building blocks of proteins. In laboratory experiments simulating early Earth conditions or interstellar space, HCN readily participates in chemical reactions that produce adenine, one of the nucleobases in DNA, as well as various amino acids. The fact that HCN exists in 3I/Atlas means it existed in the protoplanetary disk around an alien star, presumably billions of years ago when that system was forming. It means the basic chemistry that creates organic molecules, chemistry that on Earth led to the emergence of life, is active in other stellar systems as well. The universe isn't chemically isolated. The same reactions, the same molecular building blocks, appear across vast distances. Whatever star system birthed 3I/Atlas had the chemical ingredients necessary to potentially support life, at least in principle. The nickel detection adds another layer to this story. The presence of atomic nickel vapor in the coma is genuinely puzzling from a chemical standpoint. Nickel is a refractory metal, meaning it has a very high melting and vaporization point. Under typical cometary conditions, solid nickel should remain locked in mineral grains and dust, not vaporizing into atomic gas. Yet 3I/Atlas was clearly emitting nickel vapor at temperatures far too low for solid nickel metal to vaporize. The research team analyzing the VLT data proposed an intriguing solution. Perhaps the nickel isn't coming from solid metal at all. Instead, it might be bound in volatile organometallic compounds, molecules where metal atoms are chemically bonded to organic groups. Specifically, they suggested nickel tetracarbonyl, a compound with the formula NiCO sub 4, where a nickel atom is surrounded by 4 carbon monoxide molecules. This compound is relatively volatile, sublimating at temperatures achievable in a warming comet nucleus. Once released into the coma, solar ultraviolet radiation could break apart the nickel tetracarbonyl, liberating atomic nickel that then emits at characteristic wavelengths. This hypothesis found support in the observational data. The rate at which nickel production increased as the comet approached the Sun matched theoretical predictions for nickel tetracarbonyl sublimation. Moreover, the unusual sequence where nickel appeared before iron, another metal that's often seen alongside nickel in comets, could be explained if the two metals were bound in different organometallic compounds with different volatilities. Nickel tetracarbonyl sublimes at lower temperatures than iron pentacarbonyl, so as the comet warmed, nickel emission would appear first, followed later by iron as temperatures climbed further. This organometallic hypothesis has profound implications. If confirmed, it would mean That complex metal-organic chemistry is occurring in comets, creating compounds that don't exist naturally on Earth under normal conditions but that form in the cold, low-pressure environments of protoplanetary disks. It would mean that the chemical complexity preserved in interstellar objects extends beyond just simple molecules like water, carbon monoxide, and hydrogen cyanide to include exotic compounds that provide insights into chemical processes we can't easily study otherwise. The cyanide and nickel detections, combined with the carbon chain depletion and the earlier water observations, paint a picture of 3I/Atlas as a chemically complex object, simultaneously familiar and alien. It contains water, carbon dioxide, carbon monoxide, and hydrogen cyanide, all molecules found in solar system comets, and all expected products of protoplanetary disk chemistry. Yet the ratios are different, the depletion patterns are extreme, and the presence of significant nickel vapor points to chemical pathways that might be uncommon or rare in our solar system's comets. Every spectroscopic measurement adds another clue, another constraint on the formation conditions and evolutionary history of this visitor from beyond. The chemistry encoded in 3I/Atlas is a message from another stellar system, a chemical record, written billions of years ago and preserved in deep freeze through eons of interstellar wandering, now being released and decoded as the comet makes its brief passage through our cosmic neighborhood. Every star in the night sky is a sun to some other world, a gravitational anchor around which planets, asteroids, and comets might orbit. For centuries, astronomers have wondered whether other stellar systems resemble our own or whether the architecture and chemistry we see in our solar system is unique, a cosmic accident unlikely to be repeated elsewhere. The discovery and detailed study of 3I/Atlas is helping to answer these fundamental questions in ways that no telescope pointed at distant exoplanets ever could. This interstellar wanderer is bringing the chemistry of another planetary system directly to us, allowing scientists to perform detailed analyses that would be impossible for objects light years away. Consider what we know about exoplanets, the planets orbiting other stars. Since the first confirmed detection in 1995, astronomers have identified more than 5,000 exoplanets using techniques like the transit method, where a planet's passage in front of its star causes a tiny dip in the star's brightness, or the radial velocity method, where a planet's gravity causes its star to wobble slightly. These techniques are extraordinarily powerful, revealing planetary sizes, orbital periods, and in some cases, atmospheric compositions. But they have limitations. Most of what we know about exoplanetary systems comes from indirect measurements and inferences. We observe starlight filtered through an atmosphere or measure gravitational tugs, then work backward to deduce planetary properties. But with 3I/Atlas, we're not making indirect measurements of light filtered through millions or billions of miles of space. We're directly sampling material that formed in another stellar system. Every molecule detected in its coma, every isotopic ratio measured, every production rate calculated represents a direct window into the chemistry and conditions of that distant system's protoplanetary disk. It's as if another star system shipped us a physical sample for laboratory analysis, a cosmic FedEx delivery containing primordial material from billions of years ago. The chemical composition of 3I/Atlas reveals striking similarities and intriguing differences compared to solar system comets. The presence of water, detected through both hydroxyl radicals in the ultraviolet and direct infrared observations by the James Webb Space Telescope, confirms that water ice exists in other planetary systems just as it does in ours. This might seem obvious, but direct confirmation matters. Water, with its unique properties and its role as a solvent for biochemistry, is fundamental to life as we understand it. Finding water in an interstellar comet proves it's not just a local phenomenon. The molecular clouds from which stars and planets form, scattered throughout the galaxy, contain the ingredients to make water. The James Webb Space Telescope observations, conducted in August 2025 when the comet was about 3.3 astronomical units from the Sun, revealed that 3I/Atlas's coma contains not just water but a surprisingly large amount of carbon dioxide. The mixing ratio of carbon dioxide to water in the coma was measured at 8:1, meaning for every water molecule, there were 8 carbon dioxide molecules. This is one of the highest carbon dioxide abundances ever measured in any comet, interstellar or otherwise. Only one other comet, the peculiar Oort cloud object C/2016 R2, shows similarly extreme carbon dioxide enrichment. This high carbon dioxide content provides crucial clues about where and how 3I/Atlas formed. Carbon dioxide ice condenses from gas at higher temperatures than water ice. In a protoplanetary disk, there's a carbon dioxide frost line, a distance from the star, beyond which temperatures are cold enough for carbon dioxide to freeze out. There's also a water frost line, typically farther out where temperatures are even colder. The region between these two frost lines would be enriched in carbon dioxide ice relative to water ice. If 3I/Atlas formed in such a region, close to the carbon dioxide frost line in its parent system's disk, it would naturally have high carbon dioxide content. Alternatively, the carbon dioxide enrichment could result from radiation processing. If the comet spent long periods exposed to cosmic rays and ultraviolet radiation during its interstellar journey, chemical reactions on and within the ice could convert other carbon-bearing molecules into carbon dioxide. Either scenario, formation location or radiation processing, tells us something valuable about the comet's history and the conditions in its birth environment. The carbon monoxide content, measured at a ratio of 1.4 relative to water, is more typical, similar to what's seen in many solar system comets, including the previous interstellar visitor 2I/Borisov. Carbon monoxide is highly volatile, sublimating at temperatures far below water ice. Its presence indicates that 3I/Atlas formed in a cold environment where even these extremely volatile compounds could freeze out and become incorporated into the growing comet nucleus. The ratio of carbon monoxide to water helps constrain the temperature in the protoplanetary disk region where the comet assembled. The detection of hydrogen cyanide and the severe depletion of carbon chain molecules like C2 add another layer to the story. Carbon chain molecules are thought to form through gas phase chemistry in the warmer inner regions of protoplanetary disks, then get transported outward and incorporated into forming bodies. Comets depleted in these compounds likely formed in the coldest outer disk regions where such molecules were never abundant to begin with, or they formed from material that underwent different chemical processing. The fact that 3I/Atlas is among the most carbon chain depleted comets ever observed suggests it originated from the frigid outer reaches of its parent system, analogous to our Kuiper belt, or even farther out. This compositional information allows astronomers to sketch a picture of the planetary system that birthed 3I/Atlas. It was a system with a protoplanetary disk, just like the young solar system had 4.6 billion years ago. That disk had temperature gradients, with warm inner regions and cold outer zones. It had frost lines where different molecules condensed from gas to ice. Chemistry was happening in that disk, producing water, carbon dioxide, carbon monoxide, hydrogen cyanide, and various other compounds. Small grains of dust and ice were colliding and sticking together, gradually building up into larger bodies through accretion. Somewhere in the outer disk, in a cold region dominated by carbon dioxide and water ice with minimal carbon chain molecules, the nucleus of 3I/Atlas assembled grain by grain. But something disrupted this comet's orbit. Perhaps a giant planet, analogous to our Jupiter or Saturn, had formed in the system and its powerful gravity scattered smaller bodies. Perhaps the system experienced a close encounter with a passing star, gravitationally disturbing the outer disk and flinging objects southward. Or perhaps the parent star itself underwent some dramatic event that destabilized its orbiting population. Whatever the mechanism, 3I/Atlas was ejected, accelerated beyond escape velocity, and sent on a journey through interstellar space. Recent research has attempted to trace 3I/Atlas's trajectory backward through time to determine where it came from. This is extraordinarily difficult because the comet has been drifting through the galaxy for potentially millions or billions of years, subject to the complex gravitational field of the Milky Way. Stars move, the galactic potential changes, and small uncertainties in the comet's current velocity get magnified enormously when extrapolating backward over such vast timescales. Despite these challenges, one study suggested that 3I/Atlas might have originated from the border between the Milky Way's thin and thick disks, two distinct stellar populations with different ages and compositions. The thin disk contains most of the younger stars in the galaxy, stars that formed in the last few billion years from gas enriched in heavier elements produced by previous generations of stars. The thick disk contains older stars that formed when the galaxy was younger and had undergone less chemical enrichment. The border between these populations represents an epoch in galactic history, perhaps 8 to 10 billion years ago. If 3I/Atlas indeed comes from a star in this region, the comet could be incredibly ancient, potentially 10 billion years old, more than twice the age of our solar system. The implications of such extreme age are staggering. A 10 billion-year-old comet would be a time capsule from the early galaxy, when stars had different chemical compositions, when the rate of star formation was higher, when the galactic environment was fundamentally different from today. The chemistry preserved in such an object would reflect the conditions and processes active in planetary systems at a much earlier cosmic epoch. It would tell us whether planet formation in the ancient universe produced similar outcomes to what we see in younger systems like our own. Even if the age estimates prove to be uncertain, and they are highly uncertain given the difficulties of backward trajectory integration, the very fact that we can attempt such calculations highlights the value of interstellar objects. Each one is a probe of not just another planetary system but potentially of a different era of galactic evolution. The more interstellar visitors we detect and characterize, the more data points we accumulate about the diversity of planetary systems across space and time. The presence of prebiotic molecules like hydrogen cyanide in 3I/Atlas carries profound implications for astrobiology. Cyan is a key ingredient in numerous proposed pathways for the origin of life. In laboratory experiments, HCN dissolved in water can polymerize to form adenine, one of the nucleobases in DNA and RNA. HCN can react with other simple molecules under various conditions to produce amino acids. On early Earth, comets and asteroids delivered substantial quantities of organic compounds, including HCN, potentially providing the raw materials for the emergence of life. The fact that HCN exists in an interstellar comet means that prebiotic chemistry isn't limited to our solar system. Whatever star system produced 3I/Atlas had the chemical building blocks for potentially complex organic chemistry and life. If comets in that system delivered HCN and other organics to forming planets, as happened in our solar system, then those worlds would have had access to the same prebiotic toolkit that led to life on Earth. This doesn't prove that life emerged elsewhere. The origin of life requires not just the right chemicals but the right conditions, the right environment, the right sequence of chemical reactions. But it removes one potential barrier. The chemistry of life appears to be universal, or at least widespread. The detection of water, carbon compounds, and organic molecules in 3I/Atlas supports the hypothesis that the basic ingredients for life are common throughout the galaxy. Wherever stars form and protoplanetary disks coalesce, similar chemistry appears to occur. Water ice forms in the outer disk. Carbon dioxide, carbon monoxide, and organic compounds like hydrogen cyanide get incorporated into comets and asteroids. These objects get scattered by planetary perturbations, some falling inward, to potentially deliver their cargo to inner system planets. If this sequence occurs commonly, then many planetary systems might receive deliveries of water and organics during their early evolution, providing potential habitable worlds with the raw materials for life. There's another intriguing possibility suggested by recent theoretical work. Interstellar objects like 3I/Atlas, wandering through the galaxy, occasionally get captured into young planetary systems. If such an object gets captured into a protoplanetary disk around a forming star, it could serve as a seed for planet formation, rather than building up a planet grain by grain from microscopic dust. A kilometer-sized interstellar object could act as a ready-made planetary embryo. Smaller particles in the disk would collide with it, stick, and gradually accrete, potentially growing into a much larger body. This process could accelerate planet formation and might lead to planets with unusual compositions reflecting the chemistry of two different stellar systems, the host stars' disk material plus the interstellar seed's foreign composition. Whether this actually happens in nature remains an open question, but the mere possibility highlights how interstellar objects might influence not just our understanding of other systems, but the actual physical evolution of those systems. Every comet ejected from one system and captured by another represents a transfer of material and chemistry between stellar environments. Over billions of years of galactic evolution, this slow exchange could lead to a degree of chemical homogenization, spreading similar molecular inventories across wide regions of the galaxy. The study of 3I/Atlas and other interstellar objects is still in its infancy. We've confirmed only 3 such objects in human history, a tiny sample from which to draw broad conclusions. Each one has proved unique in various ways. 1I/Oumuamua with its elongated shape and mysterious acceleration. 2I/Borisov with its more conventional comet-like appearance and activity. Now 3I/Atlas with its extreme water loss at large distances, its carbon dioxide enrichment, its carbon chain depletion, and its unusual nickel emissions. As detection capabilities improve and more interstellar visitors are found, we'll develop a better statistical sense of the diversity of materials and compositions ejected from other systems. Future missions might even attempt to rendezvous with an interstellar object, as was briefly considered for Oumuamua before it receded too far. Imagine a spacecraft approaching close enough to directly sample the coma, to measure isotopic ratios with laboratory precision, to image the nucleus in detail, perhaps even to land and collect a physical sample. Such a mission would be extraordinarily challenging given the high relative velocities and limited warning time when interstellar objects are detected. But the scientific return would be immense, essentially bringing back a sample from another star system without needing to travel light years to reach it. For now, telescopes on Earth and in space continue extracting every possible bit of information from 3I/Atlas while it remains accessible. Every spectrum, every photometric measurement, every radio observation adds to our knowledge. And with each new data point, we learn not just about one peculiar comet but about the nature of planetary systems across the galaxy, about the chemistry that leads to worlds, and about the cosmic context in which life might emerge among the stars. In the span of just a few months, a cosmic visitor from beyond our solar system has rewritten our understanding of what happens in the space between stars and challenged our assumptions about cometary behavior. Comet 3I/Atlas, discovered on that July night by the Atlas telescope in Chile, has proven to be far more than just another astronomical curiosity. It has become a messenger bearing direct chemical evidence from another stellar neighborhood, a time capsule carrying materials that may have formed billions of years ago around an alien sun, now releasing its secrets as it makes its brief passage through our corner of the galaxy. The rarity of this event cannot be overstated. In all of human history, across centuries of systematic astronomical observation, we have confirmed only 3 interstellar objects passing through our solar system. 3 visitors from the vast darkness between the stars. Each one represents an extraordinary stroke of cosmic fortune, objects that were ejected from their birth systems, survived journeys through interstellar space potentially lasting millions or billions of years, and happened to pass close enough to our sun for us to detect them against the backdrop of countless stars. The odds of witnessing even one such visitor in a human lifetime were uncertain until recently. Now, with 3 detections in less than 8 years, we're beginning to understand that these interstellar wanderers may be more common than once thought, suggesting that the galaxy is filled with countless nomadic objects drifting between the stars, remnants of planetary system formation scattered throughout the Milky Way. But what truly sets 3I/Atlas apart is its behavior. The water loss rate detected by NASA's Swift Observatory shocked the scientific community. 40 kilograms of water every single second, equivalent to filling 10 large buckets continuously, pouring out into the vacuum of space at a distance where the comet should have been relatively quiet. At 3.5 astronomical units from the Sun, well beyond Mars, solar radiation should be far too weak to drive such dramatic activity. Yet there it was, losing water like a fire hose running at full blast, defying conventional models of cometary behavior and forcing astronomers to rethink how interstellar comets respond to solar heating. This unprecedented water production at such great distances suggests that 3I/Atlas either has an unusually volatile-rich composition, with highly reactive ices that sublimate at lower temperatures than typical solar system comets, or that some mechanism, perhaps an extended source of water production from icy grains distributed throughout the coma, is responsible for the dramatic outgassing. Either explanation points to fundamental differences between this interstellar visitor and the comets native to our solar system, differences that encode information about the conditions in whatever distant stellar system gave birth to this cosmic drifter. The detection of cyanide compounds adds another crucial piece to the puzzle. Hydrogen cyanide, one of the most important molecules in prebiotic chemistry, is present in this visitor from another star. The spectroscopic signatures of cyan emission, captured by powerful ground-based telescopes including the Very Large Telescope and confirmed by radio observations detecting HCN directly, prove that the chemistry necessary for complex organic molecules exists beyond our solar system. This isn't a theoretical prediction or an extrapolation from models. This is direct observational evidence that the building blocks of life, the molecular ingredients that on Earth led to amino acids and eventually to living organisms, are present in material formed around other stars. The implications ripple outward like waves from a stone dropped in a cosmic pond. If hydrogen cyanide exists in comets from other stellar systems, if water ice is abundant there, if carbon dioxide and carbon monoxide and all the other compounds detected in 3I/Atlas are present in those distant protoplanetary disks, then the chemistry of life is not unique to Earth or even to our solar system. It is universal, or at least widespread, throughout the galaxy. Wherever stars form and planets coalesce, similar processes appear to occur, producing similar inventories of molecules. This universality suggests that habitable worlds throughout the cosmos may receive deliveries of water and organic compounds from comets and asteroids during their early evolution, just as Earth did billions of years ago. The unusual chemical signatures revealed by spectroscopic analysis, particularly the severe depletion of carbon chain molecules and the surprising abundance of carbon dioxide tell us about the specific conditions in 3I/Atlas's birth environment. This comet likely formed in the cold outer reaches of its parent system's protoplanetary disk, in a region where carbon chain chemistry was minimal and where carbon dioxide ice was particularly abundant. The detection of atomic nickel vapor, possibly released from exotic organometallic compounds like nickel tetracarbonyl, hints at chemical processes that may be rare or different from what we typically observe in solar system comets. Every unusual feature, every unexpected measurement, provides constraints on the temperature, pressure, radiation environment, and chemical composition of that distant disk. This is the true power of interstellar objects. They bring us samples, direct physical samples of material from other planetary systems. No telescope, no matter how powerful, can provide the kind of detailed chemical analysis we can achieve when the object of study actually passes through our neighborhood. The James Webb Space Telescope's detection of the comet's carbon dioxide to water ratio, the SWIFT Observatory's measurement of water production, the Very Large Telescopes spectroscopic identification of cyanide and nickel, the James Clerk Maxwell Telescopes radio detection of hydrogen cyanide. Each observation adds detail to our understanding of another world's chemistry in ways that studying exoplanets from afar simply cannot match. As 3I/Atlas continues its journey, having passed perihelion on October 30th, and now receding from the Sun, it will gradually fade from view. By early 2026, it will be too faint for all but the largest telescopes to detect. Eventually, it will disappear entirely, returning to the interstellar void from which it came, bound for other star systems or perhaps to wander the galaxy indefinitely. But the data it has provided will be analyzed for years to come, yielding new insights as astronomers develop better models and more sophisticated analysis techniques. The future of interstellar object research is remarkably promising. Survey telescopes are becoming more sensitive, more capable of detecting faint objects earlier in their approach. The Vera C. Rubin Observatory, which actually captured pre-discovery images of 3I/Atlas during its validation phase, is expected to detect dozens or potentially hundreds of interstellar objects once it begins full operations. Each new detection will expand our statistical sample, allowing us to understand the diversity of materials ejected from planetary systems, the range of compositions and behaviors, and ultimately the commonalities and differences between our solar system and others throughout the galaxy. Proposed missions to intercept and study interstellar objects up close, while technically challenging given the high velocities and limited warning times, represent the next frontier. Imagine a spacecraft equipped with instruments capable of measuring isotopic ratios with laboratory precision, imaging the nucleus in exquisite detail, perhaps even collecting and returning a physical sample. Such a mission would be among the most scientifically valuable endeavors ever undertaken, essentially bringing back pristine material from another star system without requiring centuries of travel time to reach distant stars. The story of 3I/Atlas reminds us that we live in a dynamic galaxy where material flows between stellar systems, where the chemistry of planet formation is universal, and where the ingredients for life are scattered among the stars. This cosmic visitor, hemorrhaging water and cyanide as it makes its one-time passage through our solar system, is proof that we are part of a larger galactic ecosystem, connected to distant stars through the slow exchange of planetary system debris. If this journey through the science of an interstellar comet has sparked curiosity, if the idea of directly studying material from another star system resonates, then stay engaged with ongoing discoveries. Follow space agencies and research institutions. Watch for announcements of new interstellar object detections. Share these stories with others who might find wonder in the fact that visitors from beyond are passing through our cosmic neighborhood, bearing messages from distant suns. Subscribe to channels and resources that track these discoveries, because we are living in an era where the boundary between our solar system and the galaxy beyond is becoming increasingly permeable, where interstellar science is transitioning from theoretical speculation to observational reality. The universe is revealing its secrets one cosmic visitor at a time, and 3i/Atlas has just added another extraordinary chapter to that unfolding story.